So good morning to one and all. Today's myself is Ajay Shankar. And today we can go for the topic is classification of signals and their examples. Today's topic is the classification of signals and their examples. In the previous class, we seen some examples on a complete set of orthogonal, and now also using that you can take some more examples. Take some more examples on the orthogonality by using either orthogonal in signal space, orthogonal in complex functions, and orthogonal in the signals. Let us see. Take one example here. Show that over the period of interval 0 to 2 pi, show that over the period of interval 0 to 2 pi means it's a full cycle. 0 to 2 pi means it's a full cycle. A rectangular function is orthogonal to the signals of cos t and cos 2t and so on the cos nt. Means they're asking that how to show orthogonal between the rectangular function and cos function. Rectangular function and the cos function for all the integers of the values of n. The two signals is given. In that one signal is rectangular function and another signal is a cosine function. So the rectangular function I am taking from the 0 to 2 pi because they given in the interval of 0 to 2 pi only. See, the f of t I am assuming as a one signal, f of t is equal to 1 in the range of 0 to 2 pi. In the range of 0 to 0 for other and 0 for others. Means the remaining part whatever we have, that part is a 0. Understood? The another signal they're asking that x of t is equal to cos n of t. Cos n t, where n is a 0, 1, 2 and so on up to the n. So these two signals have to show orthogonal or not within the period of 0 to 2 pi only. The remaining period is a 0. So we know the formula is there. The orthogonality of the two signals, integral c to t plus t naught f of t x of t dt is equal to. Show that it is a 0, then the given two signals are orthogonal. What is the f of t here? 1 with the range of 0 to 2 pi. So small t is 0 and capital T naught is a 2 pi. So 0 to 0 plus 2 pi becomes of the full cycle 0 to 2 pi. In that the f of t is a 1 and x of t is a cos nt dt. You see here. So that is equal to 0 to 2 pi is a 0, not the t, my dear students, it is a 0. 0 to 2 pi cos nt dt. What is the integral of cos sine? And for the, we are applying the integration with respect to the t. For t, there is a constant multiplication factor is n. So cos nt Ramya 428 Ramya. Ramya. Still you are not mute your. So integral 0 to 2 pi cos n omega naught t dt. The integral of cos is a sine nt, and the denominator have that is a coefficient of the t, the n. Apply the upper limit and the lower limit is 0 to 2 pi. 1 by n. The upper limit is sine 2 pi. Lower limit is sine 0. Sine 2 pi is a 0 and sine 0 is also the 0. So 0 minus 0 becomes of the 0. So when this function, the integral t to t plus t naught f of t x of t dt is a 0, c is equal to 0. So what is a c? C is equal to integral t to t plus t naught f of t x of t dt whole divided by integral t to t plus t naught x square of t dt. The denominator is not at all equal to the 0 because it is energy signal. Energy can neither be created nor be destroyed. So only you have to take that as a numerator, only that 0 to become c is equal to 0. Okay. So the given function, the rectangular function and cos function, both are orthogonal to each other. Coming to the second one, show that the sequence, one exponential function is there, is orthogonal sequence with a periodic in n. Periodic in n, capital N it is. So they are asking that the given the one exponential signal, nothing but is a sequence. Sequence means n is varies, where n is 1, 2, so on. And capital N, whatever the capital N is given, that is a periodic. What is a periodic here? Periodic is nothing but replacing of n, the signal, let us assume x of n is equal to e power j 2 pi k n small n whole divided by the capital N small n whole divided by the capital N. Okay, my dear students. So that capital N is a periodic function and n is a variable here. For periodic function, you see, x of n small n plus capital N is equal to x of n. This is only for the discrete functions because n is a variable for the discrete. If suppose it is a continuous time function, x of small t plus capital T is equal to x of small t. The t is represented for the continuous time signals and n is represented, small n or capital N is represented or denoted by for the discrete functions only. So now I am taking here the x of n, x of a small n plus capital N is equal to e power j 2 pi k, replacing the small n as n plus capital N whole divided by n. Replacing e power j 2 pi k, here the n is there, small n. In that n, I am taking the n plus capital N. Okay, so the base is same. Having the powers is the two functions, the two terms. Split that e power j 2 pi k small n by capital N and e power j 2 pi k capital N by capital N. Both are get cancelled here. Capital N by capital N. Okay. Now, here e power j 2 pi k, e power j 2 pi k. In the previous class, I derived this function e power j 2 pi, whatever the multiplication factor is there, e power j 2 pi means always the value is 1. Always the value is 1. Why? The e power jx, you can written as cos x plus j sin x. Whatever the coefficient of x is there, you can take that as a cos 2 pi into x plus j sin 2 pi into x. Here it is a k only. Okay, here the k. So cos 2 pi into k plus j sine 2 pi into k, cos 2 pi the value is 1, sine 2 pi is a 0, it is equal to 1. So e power j 2 pi, always the value is 1. So the term here, the x of n plus 1, after replace the n as a small n plus capital N, small n capital N, you'll get the two functions, exponential functions or the exponential sequence, e power j 2 pi kn by n and e power j 2 pi k. And this function 2 pi j 2 pi kn, the value is 1. So x of n plus n is equal to e power j 2 pi kn by n is equal to x of n. So now it satisfies the periodic function. Even if you are changing the n as n plus capital N also, the given sequence, the exponential sequence is similar for both x of n plus n is equal to x of n. So x of n is a periodic with a period of n. Okay. Now, if I am taking that sequence as a two functions, let the two sequences be x k of n. K is a suffix, e power j 2 pi k n. K I am replacing here, kn by n, and x l of n. L is a suffix here, so e power j 2 pi ln by capital N. Ln by capital N. So the k, I am taking the kn. Here the L is there, I am taking the ln. Now you got the two signals, xk of n and x ln of n. Using the orthogonality of the discrete function can be checked over the interval of the period. Now we can see here. Till now we discussed about the continuous time functions only. What is the formula to find out the orthogonality? Integral we are using there. So wherever you are using the integral, see there it is a t in terms of the t functions with respect to the t only. Continuous time functions means always t. Discrete time functions means replacing that it is a t by the n, both are it is a variables only, but difference is there in the finding out the orthogonality. Integral we are using for continuous, summation we are using for discrete time functions. Remember this one. Okay. Integral for continuous and summation for discrete time functions. Now the given function is a discrete because it having the small n as a variable, as a discrete function with the period of capital N, that is also the discrete function. Okay. For this, whatever the numerator is there in the orthogonal function, as of integral till now we discussed, but here we are using the summation because the given function is a discrete function. So see here, instead of integral, I use the summation, sum of n is equal to 0 to n minus 1. N is equal to 0 to n minus 1. Why I am taking the 0 to n minus 1 is that I actually in the integral that is a t to t plus t naught. T to t plus t naught. If I use there, it is a t to the t plus, the t is equal to 0 and the t is a 2 pi, it's a full cycle. And here also it is a full cycle only. Okay. But how many number of terms you have to get? Only the n. Only the n. After expanding the summation here, it starts from the 0 up to the n minus 1 means totally it is a n. Or otherwise, if it is starts n is equal to 1 to means n is equal to 1 to what is a upper limit capital N only. Then totally you will get the n number of terms. If I using here it is n is equal to 0, to get it is a n number of terms, the upper limit I am taking the n minus 1 because the 0 is there already. Following? The 0 is there. So 0 to n minus 1 means totally it having the n number of terms. Okay. So one function is The one sequence xk of n, another sequence is xl of n. I'm taking this as a star, as a complex function. Sum of n is equal to 0 to n minus 1 e power j 2 pi k n by n. And second sequence is e power j 2 pi l n by n whole star. Okay, what is a star? Conjugate function. I am removing this conjugate here, change only the sign of the exponential power. So sum of n is equal to 0 to n minus 1 e power j 2 pi k n by n and e power minus j 2 pi l n by capital N. I'm not using here the star again because the change of the star only the change of the negative power of exponential. Understood? Simply it changes of x plus iy as x minus iy. It's a conjugate function. There is no any sign change for the real term. There is a sign change in the imaginary term only. Now the bases are the same. We can add the powers here. Sum of n is equal to 0 to n minus 1 e power j 2 pi is a common k minus l, because the minus is there, k minus l small n whole divided by capital N. That is a function we got. Let's see the next one. We know the standard formula is there. The standard formula here, that standard formula, sum of the series, infinite sum series. So one formula used here, the sum of n is equal to, small n is equal to n1, capital N1 to the capital N2. Sum of n is equal to n1 to n2, a power n, anything power n. A is nothing but here it is a exponential function. What is the formula there? That formula is a power n1 minus a power n2 plus 1, a power n1 minus a power n2 plus 1 by 1 minus a. And what is a n1? Is definitely it is always less than the n2. Less than the n2, or otherwise n2 is always greater than n1, and the denominator we have 1 minus a is always less than the 1. How to satisfy this condition? Two conditions, then only it satisfies the formula. Again, I am saying that formula is sum of n is equal to n1 to n2, capital N1 to n2, a power n, whatever the value of a is there, anything power n is equal to a power, nothing but anything, a power n1 minus a power upper limit plus 1 and 2 plus 1 by 1 minus a. That a is always less than the 1, and another condition it satisfies, upper limit is always greater than the lower limit. Understood? So in the previous equation, sum of n is equal to 0 to n minus 1 e power j 2 pi k minus l by n. It take that as a whole power n. Whole power n. Okay. Using this relation, it take that a as e power j 2 pi k minus l by capital N whole power 0. Why I am using the 0 here? Whatever the n1 there, that n1 is a 0 in this equation. What is a n2? N minus 1, capital N minus 1. So the first I'm taking the a power n1 as a 0 minus a power n2 plus 1. What is the n2 here? N minus 1 plus 1. Minus 1 and minus 1 get cancelled there. And we have the power capital N is there. Whole divided by 1 minus a. What is a? E power j 2 pi k minus l by n. Using this relation, we substitute in that, we'll get e power j 2 pi k minus l by n whole power 0 minus e power j 2 pi k minus L by n whole power capital N, and the denominator is 1 minus e power j 2 pi k minus L by n. You simplify this function, anything power 0 is a value is 1 minus e power j 2 pi k minus L, and here the power n is there and denominator is also n, and n get cancelled. And 1 minus e power j 2 pi k minus L by n. Now you can see in the numerator, e power j 2 pi, anything power is multiplication is there. E power j 2 pi is there, the value is 1. Okay, e power j 2 pi, anything, whatever it is a multiplication factor for the 2 pi, the value is always 1. So in that numerator, 1 minus 1 whole divided by 1 minus e power j 2 pi k minus L by n. So 1 minus 1 is nothing but the 0 here. So sum of n is equal to 0 to n minus 1, xk of n and xl of n whole star is equal to 0. If this condition is satisfies the 0 value, means the given function or the given sequence, the exponential sequence is orthogonal with a period of or the periodic of n, capital N. What is a new one we can learn here means, one is the periodic function, another one is one formula, the sum of finite duration. For the sum of finite duration, the sum of n is equal to n1 to n2, n1 to n2 a power n value is a power n1 minus a power n2 plus 1 by 1 minus a. And a, small a is always less than 1 and the n2 is always greater than n1. How to remove this, my dear students? It will get throughout this signals and system subject. And another one we learn here, we find the orthogonal function. We show that the given sequence is orthogonal, but the given sequence is the discrete function. What is the formula for the discrete functions or the discrete sequences? Instead of integral, what we used in the continuous time function, here we are using the summation. Sum of n is equal to 0 to n minus 1 or 1 to n, capital N. There is no any n minus 1 again. Means it reduces the n number of terms as the n minus 1 number of terms. Understood, my student? Then you can take the another example here. Find if the following signals are orthogonal. X1 of n is equal to this function and x2n of is equal to this function. What is the given x1 of n? E power j k pi by 8 into n. What is the x2 of n? E power j m pi by 8 into n. Okay. Now I am modifying this function as a simply x1 of n is equal to e power jk is already there. I'm keeping here the 2 pi by 16. So I'm multiplying the 2 in the numerator and multiplying the 2 in the denominator. After multiplying the denominator and the numerator of the power of exponential function in the two given sequences of the given signals, it becomes of x1 of n is e power j k 2 pi by 16 into n. x2 of n is equal to e power j m 2 pi by 16 into n. You see the 2 is wrote here. The two functions are the discrete functions. To prove that these two are orthogonal signals, you can use the formula, the summation, since the given functions are the discrete function. So sum of n is equal to 0 to n minus 1, x1 of n and x2 star of n. Again, you can take the complex function. What is the x1 of n? E power j 2 pi kn by 16. E power j 2 pi kn by 16. How we got the 16 denominator? You can multiply the denominator and numerator with the 2 for the given signals. And second function, I directly wrote it that by removing the conjugate, keeping the sign in the exponential, e power minus j 2 pi mn by 16. Small m into small n by the 16. So bases are same. You can add the powers. Sum of m is equal to n is equal to 0 to n minus 1 e power j 2 pi. What is the common term here? 2 pi is a common, small n is a common, and the 16 is a common. The remaining you can keep it in the parenthesis k minus m into n by 16. You see, this is the 16, my dear students. Again, you can use this formula. The sum of n is equal to n1 to n2 a power n. What is the a here? E power j 2 pi k minus m by 16. That n is whole power n. Okay. E power j 2 pi k minus m by 16 whole power 0, because n1 is a 0, minus e power j 2 pi k minus m by 16 whole power n minus 1 plus 1, because n2 is a n minus 1 plus 1, minus 1 minus 1 minus 1 plus 1 get cancelled, having the only n. Okay. So anything power 0 is a 1, 1 minus e power j 2 pi k minus m, n is a 16 here. Here the n you can take as a 16, n is a 16 because with the period of the previous example we take with the period of n. Take that 16 when n is equal to 16. When n is equal to 16, it becomes of e power j 2 pi k minus m. And we already know the e power j 2 pi is always 1. Is always 1. So the numerator becomes of 1 minus 1 becomes a 0. The given two signals are orthogonal signals. The given two signals are orthogonal signals. So with this, the totally completion of the orthogonal concept with some examples. Today we solved that is 3 examples, and in the previous class also we solved the 3 examples. Coming to the today's topic, another topic is classification of signals. Classification of signals. See, we know what are the different types of the signals: continuous time signals and the discrete time signals. So the signals classified into the 2 types. So independent variable is a function of independent variable. The time is a continuous time signals. And second one is a discrete time signals. Okay, you see the continuous time signals. It is defined as continuously with respect to the time. Continuously with respect to the time. For every instant of time. For every instant of time. And discrete time means at particular instant of time. At particular instant of time means you can see here 0, TS, TS, 2 TS, 3 TS, 4 TS, and so on. At particular instant of time means a sampling of the continuous time function becomes of a discrete time function. A discrete time signal is defined as only at specific or regular time instants. Continuous time function means at every instant of time. Discrete time function means at particular instant of time or only at specific regular time intervals. Understood? So what is the significance? We can see the analog circuit possess continuous time signals. Such circuits are operational amplifiers, filters, amplifiers, etc. And digital circuits process the digital signals. Such circuits are microprocessors, counters, flip-flops, etc. That microprocessor is one of the subject is there for the EC students and the EEE also. That will get in that microprocessor is a totally digital one. And counters and the flip-flops, the EEE students, they are in the 3rd year, they know what are the counters and what are the flip-flops that will get in the STLD. And now the 2nd year EC students, they are learning now the STLD, switching theory and logical design. They will get in the synchronous circuits. The synchronous circuits, nothing but the sequential circuits, as designed by using the flip-flops. That one of designed by using the flip-flops is the counters and the registers. The counters are the digital circuits examples only. And analog circuits is a process of continuous time signals. The given the examples of the operational amplifiers, filters, and amplifiers also. The operational amplifiers will get for the third year students. Now they are learning that is a linear integrated circuits. For the triple students, they will get in the operational amplifier 741 operational amplifier. Okay, and filters also. But for the CEC students, they are in the second year only. These topics, the operational amplifiers, filters will get in the third year, my dear students. And amplifiers. What are the amplifiers we have? Operational amplifiers in the LIC. Amplifiers will get in the EDC only. Now we are learning that. Electronic and devices circuits. These are the examples for the analog circuits and the digital circuits. Analog circuits related to the continuous time signals. Digital circuits are related to the discrete time signals. Okay. Now, see that another one, when amplitude of the continuous signal, you see, when amplitude of the continuous signal varies continuously, it is called analog signal. See, continuously. These are characteristics we have. The amplitude is continuously, there is a graph decreasing from the some value to goes to the decreasing level. For every instant of time, slowly it is decreases. When the amplitude of continuous time signal varies continuously, it is called analog signal. In other words, the amplitude and time are continuous. Means whatever the x-axis we are taking as a time, and in the y-axis we are taking as a signal x of t, having the amplitude, both amplitude and the time, both amplitude and time, both are continuous. We can call it as a continuous time. So amplitude and time are continuous for analog signals. Coming to the digital, when amplitude of the digital signal takes only finite varies, it is a digital signals. Amplitude, okay, we are taking that is a digital signal means if both the time and the amplitude is both are discrete, that we can call it as a digital signal. That only here saying when amplitude of digital signal takes only finite varies, only the finite varies, it is digital signal. But whatever the characteristics I shown here, it is not the digital, it is a discrete time signal. Discrete time signal means the continuous is sampling. After the sampling, we'll get this discrete time signal. This discrete time signal is quantized, then we'll get the digital signal. Sampling means at particular instance, at the 0, TS, 2 TS, and 3 TS, and the 4 TS. So what is a discrete time signal means? Time is discrete, but amplitude is continuous. What is a digital? Both time and amplitude is discrete. Both time and amplitude is discrete, then we can call it as a digital signal. Both time and amplitude is continuous, then it is called as continuous time signal. Understood, my dear students? These are the two signal classifications, analog signals and digital signals. Analog signals or the analog circuits process the continuous time signals, and discrete circuits process the digital circuits. Examples are operational amplifiers, filters, amplifiers for the continuous time signals or the analog circuits, and digital circuits such as microprocessors, counters, flip-flops, etc. And what is the definition of continuous time signal means? If both time that is in the x-axis and amplitude that is in the y-axis both are continuous, then it is called as a continuous time signal or analog circuits or analog signal. And discrete time signal means the time is discrete, and amplitude is continuous, then we can call it as a discrete time signals. It is also the digital signal only, or the discrete signal. And complete the digital signal means both time, whatever in the x-axis, and amplitude, whatever in the y-axis, both are discrete. Both are discrete. Then we can call it as a digital signal, or it is a finite varies. Digital signal takes only the finite varies. It is called digital signal. Now these continuous and the digital signals again classified as periodic and non-periodic signals. Again classified. The main signals classified as the continuous and the digital are the discrete signals, and these two signals again classified as a periodic and non-periodic signal. The first one. See the periodic and non-periodic. Now only we've seen one example on this also. Periodic function. That periodic means with the period of t, capital T is there for continuous, capital N is denoted for the discrete time function. Capital T is for continuous and capital N is for discrete function. You see, whatever I shown here in this slide, a signal is said to be periodic if it repeats at regular intervals. If it repeats its regular intervals, means 0 to 2 pi, there is a rectangle function. Again, for the 300 degrees, 360 degrees, it is repeating the same thing. And again, plus 360 degrees, it is repeat the same thing at regular intervals. Regular intervals means you can take let us take the example as 0 to 90 degrees. 0 to 90 degrees, there is a one signal is there with amplitude is a 1. Okay. Next, after 90 degrees also with the same amplitude, we'll get the 90 degrees to 180 degrees also. The amplitude is a 1. Now from 180 to the next value, 90 degrees also, 270 degrees, that amplitude is also the 1. And from 270 to 360 degrees is also the amplitude is 1. Means for every 90 degrees, it repeats the signal. It repeats the signal. Okay. If it repeats the signal, then we can call it as a periodic with the period of that value as a 90, 90, 90. With the period of 90, it is repeated. The period of 90, it is repeated. That only a signal is said to be periodic if it repeats at regular intervals. If it repeats at regular intervals. A signal which repeats after every time interval. After every time interval. This is another definition for the periodic. A signal which repeats after every time interval of t. That t I assume the 90 degrees. For every 90 degrees, it is repeats the same amplitude. Or the same signal, not the amplitude I am saying, the same signal. If suppose the 0 to 90 degrees is a 1, from 90 degrees to 180 degrees is a -1, means it is not the periodic. Because it changes the amplitude as a plus to the minus. It is not the periodics. Okay. For every time interval of t, capital T, is called periodic signal. If x of t is called periodic, if and only if x of t plus capital T is equal to f of x of t for all the values of t. That capital T is a constant, but small t is a variable. These are formulae that satisfies the given signal is periodic signal, that too continuous. That too it is a continuous time signal. Now see, for the discrete time signals, a signal is x of t for which there is no value of t satisfies the condition. If no value of t satisfies the condition, is called non-periodic. So x of t plus t is not equal to x of t, then it is a non-periodic signal, my dear students. For discrete C, the x of n plus capital N is equal to x of n for all the integers of n. Okay, these are formulas for continuous and the discrete. X of t plus capital T is equal to x of t is a formula or the condition for the continuous time signal as a periodic. And this equation, x of n plus n is equal to x of n, is a condition for the periodic, for the discrete time signals. What is the capital N and what is the capital T? Okay, to find out the frequency or the angular frequency, you can say. The frequency, you know, the inversely proportional to the time period. F is equal to 1 by T. You can multiply the two, both sides, 2 pi f is equal to 2 pi by T. What is a 2 pi f? Angular frequency omega. So the angular frequency omega is equal to 2 pi f, that is equal to 2 pi by T. Cross multiply the two functions as a T is equal to 2 pi by omega. T is equal to 2 pi by omega. We already had this equation. So that is a full cycle. The T is equal to 2 pi by omega with the interval of T is equal to 2 pi by omega. The given signals are orthogonal. We already did some examples also. Whenever if there any example, the given the T is equal to 2 pi omega means the interval is full cycle. That is 0 to 2 pi. Okay. And similarly, as an angular frequency in the discrete, the notation that denoted as a omega, it is angular frequency. Okay, for the discrete is 2 pi by n and n is equal to 2 pi by omega. So both are the same, but representation is different. The T, the capital T is equal to 2 pi by omega, as regularly we are using this omega for the continuous functions. For discrete time functions, instead of capital T here, the capital N and 2 pi by omega, and the omega representing in the digital is different than to the analog functions. Both are the same. N is equal to 2 pi by omega and capital T is equal to 2 pi by omega. The denominator omega, so both are angular frequencies only. Understood, my understood. Is a periodic and non-periodic. When we can say it is a non-periodic, if this condition is not satisfied, x of t plus capital T is equal to x of t is not equal to x of t, is called non-periodic signals. So again, you can see, read out this one. A signal x of t for which there is no value of t, there is no value of capital T, satisfying the condition x of t plus t is equal to x of t is called non-periodic or aperiodic signals. Okay, aperiodic signals. Similar way here also for the discrete, there is no value of capital N satisfies the condition of x of small n plus capital N is equal to x of small n. That is equal to means I use there, it is a no value of, if I am not using that, there is no value of n satisfied, then you can use this function as x of n capital N is not equal to x of n. Understood, my dear students? So note here, sum of two continuous time periodic signals, they may not be periodic. Sum of two continuous time periodic signals may not be periodic. Another one, sum of two periodic signals is always periodic sequences. So why it is a sequence I am saying here, the sequence we are using for discrete and continuous time functions is for the continuous. Okay, sum of two continuous functions may not be periodic, but sum of two periodic sequences is always a periodic. These very, very important bits in the online examination point of view, my dear students. You can read out this. The sum of two periodic signals is periodic only if the ratio of their respective periods is a rational number. Suppose the two signals is given. In that two signals, you can take what is a mutual period for the two signals is you can take it as a ratios of 2. For the first signal, the period is a T1. For the second signal, the period is a T2. The ratio of the two signals, T1 by T2, is the rational number for the common period for the two signals. Sum of two periodic signals is periodic only if the ratio of their respective periods is a rational number. Okay, the T1 by T2 for the continuous. For the discrete is N1 by N2, simply it is. Okay, for the fundamental period is the LCM of T1 and the T2, least common multiplier. And the fifth point, you can see if the ratio of T1 by T2 is an irrational number, then the signal X1 of T, X2 of T do not have any common period. If it is a rational number only, then only we can say it is having the periodic signal or the period. For the periodic signal, it is a period you have. If it is not the rational number, it is an irrational number. There is no any common term or the common period for the X1 and the X2 or X1 of T and the X2 of T. These are the very, very important points when we go for the periodic and non-periodic signals. For the two, some of the two continuous time signals may not be a periodic, but the sum of the two periodic sequences means for the discrete or periodic signals. And if the two periodic signals, the common period is taking off the ratio between of the two signals, if it is only the rational number. If it is not the rational number, there is no any common period for the two signals. Remember this one. See, there is a three characteristics I wrote there, I draw there. One is showing that it is a periodic signals. See, with this period, here to the here, I'm taking the full cycle. From here, let us 0 to 2 pi, 0 to 180 degrees, or 0 to 90 degrees. Okay, whatever you can observe, for every 360 degrees you can observe, it is repeated. Okay, 360 degrees means let us take this point to this point, full cycle. And again it is repeated for the 360 degrees. Again it is repeated. And in the second characteristics, second figure, you can see a sawtooth wave is there. And it is repeated for every time period of t, 0 to t, and t to 2t, and previous also minus 2 to minus t to 0, minus 2t to the minus t, and again it is repeated. It is one example of the periodic signal. And here also you can observe here, from 0 to the value is slowly it is decreases, and again slowly it is decreases for the 4 samples, and here also the 4 samples slowly it is decreases. Means for every 4 samples it is repeating. 4 samples means what is the capital N there? Capital N is equal to 4. Understood? The value we can take any as a sine wave, or it is a sawtooth, or it is a gradually it is decreases the functions. It is repeated with the period. It is repeated with the period. Then we can call it as a periodic signal. In this shown the 3 figures. Now see, the first one is a continuous, because both the time and amplitude is a continuous. Then we can call it as a continuous time signal. Second figure you can observe, time is discrete here, 0t, 2t, minus t, minus 2t. Time is discrete, but amplitude is, see here the continuous is slowly is increasing up to the t, and again it is a 0, and slowly it increases up to the 2t, and it is decreases. So second function shows a discrete function, and the third function is also shows the discrete function only, because time is discrete and amplitude is a continuous. Okay. And second, here the 3 examples are there for the non-periodic signals. That non-periodic signal and 0 to t minus t, it is not repeating with the again full cycle is a 0, and minus 2t minus t to t, it is not repeated here from t to another one, and minus 2 to the left hand side because it is a zeros. We can't say this is a periodic signal. Periodic means it is repeated with the same interval. Okay, these three examples shows a non-periodic or aperiodic signals. A non-periodic or aperiodic signals. Understood? That is the one classification of a discrete and the continuous time function. Another classification, even and odd signals. Another classification is even and odd signals. Even. What is a even means? Example of even is cosine function. Example of odd function is sine function. Why? Cos of minus theta becomes of cos theta. So the cos is a even function. And what is an odd signal? Sine signal is an odd signal. Why? Sine of minus theta, nothing but minus sine theta. Okay, for positive values and the negative values, both values you can take, we'll get the positive values only. Then we can call it as a even signals. For the negative values, you'll get the negative sine values. Then we can call it as a odd functions. See, a signal x of t or x of n as a continuous x of t, a discrete x of n are said to be even signals if it satisfies the condition. If it satisfies the condition, what is that condition? X of minus t is equal to x of t for all the values of t. And x of minus n is equal to x of n for all the values of n. But coming to the odd functions, a signal is x of t or x of n is said to be odd signal if it satisfies the condition x of minus t is minus x of t. X of minus n is equal to minus x of n. So sine function, tan function, these are all, it is a odd function. So, okay, if you know the cos is a odd even function, sine is a odd function. So what is a tan? Sine by cos. Sine is a odd function means definitely the tan is also the odd function. See the example here, even cosine signals are symmetrical and the sine signals are asymmetric. Vertical axis of the time origin, whereas odd signals are asymmetric. Symmetric and asymmetric. Symmetric are cosine functions, asymmetric are the sine functions. Okay. And these even functions and these equivalent functions again having a combination of even and odd functions. The sum of the two signals, odd and even, let x of t is equal to, first term is xe of t as an even function plus xo of t as an odd function, continuous, and discrete is represented x of n is equal to xe of n as an even function, the first term, plus xo of n as an odd function. Okay. What is the xe of n from these two functions? Xe of n is equal to adding of two functions. Adding of two functions, xe of n is equal to 1 by 2 x of n plus x of minus n as an even part. Xo of n is equal to the difference between of the two functions. 1 by 2 x of n minus x of minus n. 1 by 2 x of n minus x of minus n. Okay. And similarly, xe of t, 1 by 2 x of t plus x of minus t is a continuous. Xo of t is equal to 1 by 2 x of t minus x of minus t. Understood, my dear students? How will you get this function? You can add x of t and x of minus t. Substituting the minus here, x of minus t, xe of minus t plus xo of minus t. What is x e of minus t? X of t on. So x e of t minus x o of t. So taking off these two functions and you can add, you'll get the even part. And taking off these two functions, you can subtract, you'll get the odd part. So one function, the even part and the odd part value is 1 by 2 x of n plus x of minus n. Odd part is x of n minus x of minus n. Okay. The product, the even signals and the odd functions. Even is a cosine. See here, the characteristics is represented as a cosine function, and here the even function is a sine functions. Okay, the sine waves, the full cycle, the sine wave here from 0 to, and this is a cosine waves. The product of two even and odd signals is an even signal. Product of even and odd signals. The product of an even signal and odd signal is a odd signals. Okay, even or odd signal, even and odd signal. Understood? Plus into minus and minus into plus, plus into plus and minus into minus. Understood? Let us take this, the plus is even and the minus is odd. Plus into minus, you'll get the minus only, or minus into plus only is a minus. But plus into plus is always a plus. Minus into minus, you'll get the minus. Okay. In the tomorrow's class, we've seen that is a classification of signals is only the two, continuous and discrete. And these continuous and discrete functions again classified as periodic and non-periodic, even and odd signals. In the tomorrow class, we have again the another classifications are there, the continuous and the discrete functions, the two, the discrete and the deterministic functions that we can see in the tomorrow's class. Okay. That is deterministic and random signals and energy and power signals, my dear students. These are the another two classifying of digital and the continuous time signals. We already discussed about two, periodic and non-periodic and even and odd, and another two subdivisions of the continuous and the discrete signals classified as deterministic and random signals and energy and power signals. Energy and power signals. In the tomorrow's class, we can see this, what is the deterministic and random signals and what is the energy and power signals. Okay. If anybody have the doubts up to the today's class, you can please raise your hand and ask the questions. I will clarify your doubts. Okay, my dear students, thank you one and all.